Okay, so again, the basic machine learning setting, we have a bunch of data points and we collect them into a feature matrix X and a label vector Y. And we would like to learn a linear model, for example, which is parameterized by a weight vector. So what we do is we want to minimize the training error. The training error we can represent compactly as this squared Euclidean norm. And we try to solve this using, for example, some .fit function. Okay, so far so good. But in practice or in many applications, you're not having one single data set and one single model, but rather you have a collection of local data sets. So we have one local data set, one weight vector, one feature matrix for each node, one label vector for each node. So here we have node I. I call this a node I, and here we have another node I prime. So we have a bunch of local data sets, and each local data set is characterized by its own feature matrix or local feature matrix and local label vector. Okay, so this setting is useful whenever you have distributed data. Does some of you have an application in mind or work on an application where you have such distributed data? So you cannot really reasonably model the data set as one table or one matrix, but you have rather a collection of data sets. Hospital, yeah. So this local data set could be one hospital. Pardon my drawing skills. So there's a reason why I didn't went into art school. A hospital, and this is one of the first applications of federated learning because it allows to train such models. So by the way, we not only have local data, but we also have local model parameters. So we have a separate model parameter for each node. And in federated learning methods can train these parameters. So we have a whole collection of parameter vectors, one for node I, one for node I prime, without exchanging raw data. So that's what makes federated learning interesting, because the standard solution, and sometimes it might be the best solution, you store this data set on a hard disk or some memory device, memory stick, this data set on a stick, put it into your car and drive to the computing center. This might be the best solution for some applications, but for other applications, it's not the best solution because you should not share raw data beyond the hospital. Only something like model parameter updates, and this is what we will see how what federated learning does. It shares model parameter updates, but not raw data. Okay, so one applications is hospitals. What could be another application where we have local data sets, collections of local data sets? Weather, yes, you will. How do you know? FMI stations or weather in general, weather. We have weather stations. Weather stations. And we would like to train a forecasting model for a specific location, like now for Helsinki. But the Finnish Meteorological Institute also takes measurements in the north, in Oulu or Rovaniemi. And maybe it also contains useful information for our model here in Helsinki. So we might also use federated learning, and you will use federated learning in the coding assignments for weather stations or weather data. What other applications do you have in mind? This could be topics also for your federated learning project, for those of you who want to upgrade the basic variant to a 10-credit variant. So what cool application do you have in mind for federated learning? Internet of Things, so sensors or general devices that generate data and somehow are connected. So this is basically every piece of electronic nowadays that you have on some. So I heard a while ago that a manufacturer for car industry, Bosch, German manufacturer. They also equip their devices with sensors, small sensors, and basically on every car, Mercedes or other cars, not to make any advertisement. I don't have a Mercedes, unfortunately, but they collect data. So each local data set is a car. And you would like to learn a model for each car, like, is there an obstacle in front of me and should I now take the brake? But you could use, of course, the observations from other cars, and you possibly should for improving your collision detection algorithm. So cars. Something else? What could be a federated learning application? A what? Finance. Yes, finance. Different financial institutes generate data, and you want to learn based on all the information. For example, if there's if this new restaurant here, which is always empty, is, for example, a money laundering pit. Okay, so yeah, in general, whenever you want to personalize something, personalization, because a local data set could be a person. For me, for example, I generate data with my now Google Fit app. I found out they also track when I go for a walk. Basically, every step I do is tracked by Google, which is very cool and scary. But so Google collects these local data sets for each person, and they could use this data to train a tailored model for me. For example, would I be interested in this Google product? So whenever you want to personalize models, federated learning might be a useful technology for this, because we will see that the federated learning algorithms federated learning algorithms, they really train a separate model for each local data set. So this W hat here at node I and node ij is different in general. So you let each local data set affect, or you use each local data set to train a local model. Okay, so far so good. So what was in basic machine learning, the main data structure, which were numeric arrays. So we had a feature matrix X and a label vector Y. And in Python terms, we use which types or which kind of objects typically to store the feature matrix and the label vector? NumPy arrays, numeric arrays. Numeric arrays. And now in federated learning, we extend this to federated learning. We have a whole network or a graph with nodes being local data sets. And on each node, we have a local feature matrix and a local label vector and a local weight vector. And again, so these local quantities we can store with numeric arrays, but we need something that binds those together. So if any one of you already looked into the lecture notes or the coding assignments, what Python object will we use in this course to bind those together, this network of local data sets?
We use the graph class from the network X class.
Yes, network X. So we use network X objects. This is now the second main library, Python library we use, network X. Network X dot graph. This class will be our main friend here. And so this, what I really appreciate about this network X. By the way, how many of you used network X already in Python? Oh, very good, very good. So I guess you already appreciate this flexibility, because you can attach to each node in a network X graph basically anything you can define in Python, including NumPy arrays, including not only NumPy arrays, but any scikit-learn class. Like what scikit-learn class did you use for training machine learning or for doing machine learning? Linear regression. So you can attach here a linear regression You can store a linear regression object here, this node, and at another node, you could store another scikit-learn class object. What other scikit-learn classes do you know? Rich regression. So here we could attach a rich model. And here we could add a decision tree. So this is pretty neat, this network X. However, in this course, we will do basically dry running, or like, let's say we make a simulation of a network, because everything is on our single laptop. And when you're on your single laptop, then this network X graphs are really handy. But I'm not sure, maybe there's already some implementation that takes a network X graph or network X code, and you can distribute it where nodes of the network X graph are on different computers. Does any one of you know such a package on top of network X or below network X? No? So if I'm not completely wrong, you will hear about one such package in a guest talk by Flowers. So we will have a guest talk, I think, in April or end of March. We will have a guest talk by Flowers Lab, a company that builds such software. And as I understood, this should basically allow to take a network X code or code that uses network X graphs and automatically distributes the nodes or implements the nodes of the network X graph on different machines, which is pretty neat. Okay. Any questions at this point? So the main object now, the mathematical object, is the empirical graph for the rest of this course. Empirical graph. And this graph has nodes, which we index by index I, and we use the first n numbers. So the nodes are always, the node index is always a natural number, and the number of nodes is the last index. So here we have 3 nodes. So the node index goes from 1 to 3. Okay. So far, so good. We attach to each node, we attach a feature matrix, xi, and a label vector yi. And yeah, we focus on parameterized models. So I have here teased you a bit or tried to impress you with this wild combination of models. So here, decision tree, rich regression, linear regression. We will not focus too much on this really fully heterogeneous networks. This is subject of my current research. But in this course, just to get started, to do the first baby steps, we use only parameterized local models. So we have a parameter vector. In particular, we will focus on linear models. So for each node here, we want to learn a linear map that predicts well the label of a data point based on its features. Okay, so far so good. So that's about the nodes. And then we have edges. So an empirical graph is an undirected graph. So the edges have no sense of orientation or direction. So for example, this edge here is connecting node 2 and node 3. And it's the same as the edge connecting node 3 with 2. So within this course, using this concept of empirical graphs, we can only model symmetric relations. So if node 3 is in a relation, I will talk about in a second what this means, with node 2, then node 2 is in relation with node 3. This might not always be sufficient. So this is just one type of model. And in some applications, you would like to have asymmetric relations to model like causality. And but this is beyond the scope of this course. Okay, undirected, and we have weights. So this is now a bit of a challenge because this I call these weights of linear regression always parameters in the nodes to distinguish it from the weights of an edge. So for each edge, we have a weight, which is non-negative. And this edge represents a coupling between the model at node 3 and node 2. and the weight is the strength of the coupling. So it's the strength of the coupling between W, so the parameter vector at node 3 and parameter vector at node 2. The larger this weight, the more we want to couple those two. So it's like the settings here, or the mindset is it's a design choice. We choose an edge to do something. It should couple the training. We will see then later that for this to be useful, the edges should somewhat reflect the statistics of the data sets. So it only makes sense to couple the training of two personalized models if for example, for persons, if they are similar. So for example, if you couple my model with the personalized training model for a 10-year-old girl, then this might not be very useful. But if you couple my training data with somebody else from Austria, 20 years old, and 60 kilograms, then it might be more useful. So we will see then in a later lecture how to find those useful edges using graph learning methods. These graph learning methods, they try to find data sets that have similar statistics. By the way, does any one of you know, would any one of you have any idea where to start when you have the task to test if two local data sets are from the same distribution? Or would this be completely... yeah.
Well, I mean, if we hypothesize the two data sets to be from a normal distribution, I guess some kind of normality test.
Yeah.
Could be in order.
Yes. So we have here a data set, a local data set, and we have here at node 2 a local data set. So you have two local data sets that you could store in two tables. Does any one of you know about tests that could find out or give us some idea if these two data sets are from the same underlying distribution? Did any one of you hear about two-sample tests? T-test, yes, T-test, for example. If some of you have studied bioinformatics or something related to biology, I guess there you mess around a lot with these tests because you need to find out if this data set really follows some other distribution, or if the data that you collect comes from the same distribution. And one variant of this problem is to find out if two data sets come from the same distribution. And there's something called the t-test. So there is hope. There is hope that we could get useful choices for these edges. But for this lecture, we assume we have this engineering expertise, so we know where to put the edges. By the way, let's say if this is an FMI station, a weather station, would you know some intuitive way to find out if you should connect or should couple the training of models for FMI stations? What could be a good indicator or criterion to couple two FMI stations? The distance, yeah. We know for each FMI station, you know the latitude and longitude. So you can measure the distance directly using Euclidean distance, using latitude and longitude, and connect each FMI station with the nearest neighbors. Okay, are there any weather gurus here who would challenge this approach? Yes.
So in addition to spatial distance, it is also important to consider whether the geographical environment of the two weather stations are similar. For example, one weather station can be in a valley and one can be on the top of a hill.
Yes, exactly. Very good. So there's other things. So if you look, for example, at Finland, so you clearly see here the shape of Finland. Again, please, I didn't study arts for a reason. But let's say here is Turku, more or less. And you would say here is, what is here? Lappeenranta. And here is Oulu. So you would say Lappeenranta is very far away from Oulu, but regarding latitude and longitude, but a weather guru might say, but Lappeenranta might actually be more similar to Oulu than here to Tampere, because Lappeenranta and Oulu, well, Lappeenranta almost is at the coast. So it has a coastal climate. So you see that using only latitude and longitude might be misleading, and you will see that in the graph learning lecture and exercise that you could do better by looking only at the data itself. So you will then look at the weather data and see that the weather data tells you that Lappeenranta is closer to Oulu statistically than to Tampere, for example. Okay, any questions at this point? So this is the crucial stage always when I write a paper about federated learning to convince the reviewer that there are ways to get the empirical graph. So I assume a lot in my papers, somebody gives us the empirical graph and the reviewers then are very critical. So who gives you the empirical graph? And I'll try to convince you. Is anyone not convinced yet that you can get easily an empirical graph? Well, in the end, it's a design choice. In the end, it's really a design choice. You, the federated learning engineer of the future, you choose which nodes you connect. Sometimes you don't have so much choice because the connection depends on a Wi-Fi and a wireless communication link, and it's blocked. So then you can write down on your paper the plan. These two are connected, but there is no connection in reality. So maybe it should also reflect, this design choice should reflect the communication ability. So in more general terms, the computational infrastructure. So we will learn federated learning algorithms that could be run on each node could be a smartphone. And the algorithm computations, they require to be transmitted between the nodes. But if there's no connection, then it doesn't make any sense if you have here an edge because you cannot implement it. Okay, that's about the empirical graph. I wanted to say, and yeah, now we need to do we need to develop a bit more mathematics. So if we look at an empirical graph, or did I already generalize people? So we want to somehow characterize the connectivity. So if this node I equal 1 and node I3 are strongly connected. And one way would be to count paths or to somehow count the direct links between those two nodes. So they are very intuitive ways to measure connectivity. Did any one of you study already connectivity measures? Yes. Which connectivity measure did you hear about? Distance. So how many hops do you need to get from node I to node 1 to node 3? It's one measure. But we will use a different approach, which is based on the Laplacian matrix. So it is very useful to define a Laplacian matrix for an empirical graph. So this is an empirical graph. We have here edge weights. And so how many of you know how the Laplacian matrix of a graph is defined? So I step through it. So in this case, the Laplacian matrix is a matrix with 3 rows. So one row corresponding to each node and one column corresponding to each node. So each row corresponds to a node, the first row to node 1, second row to node 2, and third row to node 3. And similar, the columns, because Laplacian matrix is symmetric. So L equals L transposed, it's symmetric. And it's defined as follows. For each off-diagonal entry, you put minus the edge weight if there is an edge between those two nodes, minus I2, and here minus A2. Between node 1, so this is this first column, and node 3, which is the row 3, there is no edge, so there's a 0. And on the main diagonal, you put the negative of the sum of all off diagonals. So this is A1, 2. And here we have node 3, 2 is minus A23. So here we have to sum A12 plus A23. Okay, and between node 2 and 3 is again minus A23, and the node 3 has only one edge, so we have here A23. So far, so good. And it turns out that this matrix tells us a lot about the connectivity, about the global connectivity structure, and in turn, it will tell us a lot about the learning methods or the statistical properties of the federated learning methods that we will formulate in a second. But let's explore a bit the properties of this matrix. So the Laplacian matrix is symmetric, as I said. It has real valued entries. And what can be seen immediately, that the sum over any row is 0. So if you sum the entries in the same row, you get 0. And similar, because it's a symmetric matrix, the same applies to a column. So the sum of all the elements in the same column is 0. Yep. In mathematical terms, we can formulate this as if you apply the Laplacian matrix to a vector that only contains ones, so this is also defined in the notation section of my lecture notes, this vector contains only ones, then you obtain 0. And this means that the vector 1 is an eigenvector of the Laplacian matrix. Always, by the construction itself. The vector 1 is always an eigenvector of the Laplacian matrix with eigenvalue 0. Okay. By the way, this means, what is an immediate implication of this fact? That there is an eigenvector with eigenvalue 0. What can we immediately say about this Laplacian matrix? Oh, yeah, several things we can say, but we can say it's not invertible. Because there's a vector that if we apply the matrix to this vector, we get 0. So the null space is non-trivial. Okay, that's interesting. But let's continue our exploration of this Laplacian matrix. So sometimes I forget this superscript here. Please bear with me. I like to indicate that the Laplacian matrix is assigned to a certain empirical graph. So with this superscript, I indicate the graph to which it is assigned. Okay. It is also, one can show that if you look at the local parameters, so we have here a local parameter vector here, a local parameter vector here, and a local parameter vector here, that the graph Laplacian allows to measure the total variation of these parameter vectors. So what's the total variation? The total variation, as the name hints, measures how much do the parameter vectors change or vary over edges. This is what we don't want, actually. So this is what we will penalize in our federated learning algorithms, because remember, an edge should couple the training, for example, here of this parameter vector at node 1 and parameter vector at node 2, or equivalently, we want to have this variation between these two small. And we measure the variation using the squared Euclidean norm. And the total variation is the sum over all edges. So in this case, we have only 2 edges. So the total variation is plus W2 minus W3. And we also bring in the edge weights. So the larger the edge weight, the more we want to couple the model parameters. So we use this to scale this variation term which we want to penalize. So if we have a large weight here and we multiply this with the variation, so getting a small total variation requires us then to really force those two to be close to each other such that this squared Euclidean norm is small. Okay, and it turns out that this total variation can be written equivalently as a quadratic form using the graph Laplacian or a tensor product of the graph Laplacian. So for simplicity, let's assume that each parameter vector consists of one single entry. So the parameter vector is one single parameter, and then I can avoid here this Kronecker product, and I have a much easier life here in the lecture. You will find then in the lecture notes the general case where we have more than one parameter or parameter vector. Yeah, and in this case, this squared Euclidean norm becomes the difference squared. Yeah, I should have thought about this earlier to make my own life easier here. So I consider the special case where each parameter vector consists of one single parameter. And so then this total variation turns out to be equal to this quadratic form, where in this quadratic form, we use the stacked parameters for each node. So we take the parameters for node 1, take the parameter for node 2, take the parameter for node 3, and stack it into a big matrix. And we can also do this if this is not a single parameter, but a parameter vector. We then chunk together the local parameters. Okay. Yeah, so it turns out that this Laplacian matrix allows us to write the total variation, which is what we want to penalize. We will use as a penalty term. And we can write this total variation as a quadratic form, which is nice mathematically. We will again end up with quadratic optimization problems, like we did for linear regression, like we did for ridge regression. Okay, but just from this fact that this quadratic form equals total variation, we can tell immediately another property of a Laplacian matrix, which is this quadratic form is always equal to total variation, and total variation, as you see it here, is always a non-negative real number. So if this quadratic form for any vector w is always non-negative, what does this mean? Yes, again, we have a positive semi-definite. Okay, and what does this mean? So what is the coolest result? What is the coolest result of linear algebra? That I praised so much? Eigendecomposition or spectral theorem. Theorem, which is this Laplacian matrix can be written as lambda 1 times rank 1 matrix with U1 till lambda n U. Okay, I use superscripts UN. And these lambdas here, these are the eigenvalues. So lambda 1 is smaller equal than lambda 2, is smaller equal than lambda 3, blah, 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 blah. Yeah, in this case, we only have 3. And what is the smallest eigenvalue from what you see on my sketch? Lambda 1 is, what is the value of lambda 1? 0, yes, because they must all be non-negative, because it's a positive semi-definite matrix. They must all be non-negative, but we have seen already that 1 is an eigenvector with eigenvalue 0. So this actually is an equality, and this is true for any Laplacian matrix. So the smallest eigenvalue is 0. So this tells us that the first, yeah, and the eigenvector, the corresponding eigenvector is 1. So completely identical parameters for each node. Not really useful, or doesn't give us that much information about the connectivity, because for any connected graph, or for any graph, the smallest eigenvalue is 0, and the corresponding eigenvector is all identical. All local parameters identical at all nodes. So this is basically the standard machine learning setting. We just clone the one model for each node. There's no difference. So what is really interesting is this second eigenvalue. And I would say that spectral graph theory, the whole field of spectral graph theory, is about studying this second smallest eigenvalue. It tells us a great deal about the connectivity and in turn about the statistical properties of federated learning algorithms. So, for example, if lambda 2 is also equal to 0, so we find another eigenvector u2 u2. We find an eigenvector u2 that is different from all constant eigenvector and also has eigenvalue 0. Then this means lambda 2 is 0. And in this case, what can we say about the graph? It must contain at least 2 components or 2 subsets that have no edge between each other. For example, this happens for a graph that looks like this. So here's one component or one subset, and here's another subset, and there's no link between those two. And this happens, or this we see directly from the eigenvalues. If we find a second eigenvector with eigenvalue 0, which means lambda 2 is 0, then the graph breaks down into 2 components, at least 2 components. There might be more, because also lambda 3 might be 0, which means there are then 3 components. But we don't go beyond. So because our focus is on the case when lambda 2 is larger than 0, and this means the graph is connected. So we can find a path from each node to any other node. And moreover, it measures also the connectivity. So it gives us not only a quantitative statement, which is not only a qualitative statement, which is as soon as lambda 2 is larger than 0, key is connected. So this is like a qualitative property, but also a quantitative statement. In particular, lambda 2 measures the connectivity of this graph, and this can be made precise by a lower bound that I have worked out, or have that I discuss in the lecture notes. And this lower bound is, so the total variation in this case, so let's look at our case. The total variation in general is the sum over all edges in the empirical graph. So this is the edge set. We use the edge weight times the square of the difference, so the variation of the model parameters attached to this edge. And this is larger or equal than lambda 2 times the sum of squares of the local parameter minus the average. So this is the average of these local parameter vectors. So this lambda 2 allows us to lower bound the total variation in terms of the deviation of the local parameter vectors from its average. So this average here is just the average over all nodes. So let's see, we have node I equal 1. So this is the average. This is, so to say, the mean of all the local model parameters. And this here is, I would call it maybe the how would you call it? Did any one of you have courses on signal processing where you have the AC component? So you can decompose a sequence as a constant signal, constant values, and the rest. So this is basically the varying or the variation component in the local model parameters. So the more the variation is in this local parameter vectors, the larger is the total variation measured across the edges. And it will prove very useful, this inequality, for analyzing the statistical properties of federated learning algorithms. Okay, I suggest we have now a short break till 5:05. Okay, so the last part of this lecture is now dedicated to the federated learning principle that I was announcing so much. So it's called generalized total variation minimization. And it's based on an empirical graph. So you must represent your application or your data set by an empirical graph. Here we have, for example, 3 nodes. And at each node, each node carries a local data set given by a feature matrix label vector and a parameter vector for a linear model. So how would we learn this parameter vector for a local data set individually? Well, we could try to minimize over WI this training error. And we can do this for all W's in parallel. So this decouples. So we could also, minimize the sum over all nodes. And this would decouple. If we want to minimize this sum over the individual local parameters, then we just individually minimize these terms, and then the sum will also be minimal. So there would be no coupling. And now we bring in the coupling using the similarity graph. So we want to enforce the model parameters to be similar across edges. We want to couple them across edges. And this is equivalent to penalizing or regularizing using a measure for their variation. So we want the variation to be small over edges. So we penalize a variation over the edges. So we penalize the total variation. Okay. And that's it. So that's our federated learning design principle for the rest of this course. It's actually an instance of regularized empirical risk minimization. So this term here is a regularizer. And we still have the interpretation of alpha. So this regularization parameter, or let's call it GTVMin parameter here. This controls the amount of penalization or the strength of the coupling. The larger alpha, the more we penalize a variation of the model parameters across the edges. So if we make alpha very large, any solution to this, so I call the solution W hat, any solution to this problem will be almost constant at all nodes. So this corresponds to what is called single model federated learning. So we have a distributed data set, but we want to train and we want to train a single model. So and this is equivalent to having all nodes having a copy of this single model. So we would like to have W hat 1 equals W hat 2, W hat 3. So this means a single model, or each node has a copy of this single model. And we can enforce this as a special case of this GTV minimization using alpha very large. Alpha very large. Results in the solutions to this problem being identical local model parameters. There might be some applications where this is useful. Like in healthcare, we would like to learn one single model that predicts a certain disease from symptoms in the same manner for all patients. But we train this model using distributed data that is held by different hospitals, and we don't want to share raw data. So what we could do is we solve this GTV minimization problem with alpha very large, and we can solve this optimization problem using gradient descent, which we will talk about next week. So next week on Monday, I will introduce you to this maybe most important class of optimization algorithms for machine learning and federated learning, which is gradient-based methods. And these gradient-based methods can be implemented as message passing. So we have to exchange messages which are not raw data, but something like model parameter updates. Okay, but there might also be other applications where we don't want all model parameters to be identical. So here we could use alpha moderate. Use an alpha moderate value for alpha, and then we allow this different model parameters or different nodes to change, to be a bit different. We will also see that sometimes you have a specific structure in this empirical graph, like a cluster structure. So you would have a subset of nodes which are very strongly connected, like all Austrians using this fitness tracker. And you would use you would like to learn the same model for all the Austrians for some reason, because they all like alpine skiing. And there you can find value ranges for alpha that do exactly this. So you will learn the same model for all nodes in the class, in the same cluster. This is also known as clustered federated learning. We will hear about this in a later lecture. And this clustered federated learning also corresponds to a certain value range for this alpha. So alpha not too large, because if it's too large, we would learn for all nodes in the network the same. But if we make it a bit smaller, we only learn the same model on well-connected subset of nodes. Yeah, and then there's the other extreme, alpha very small, or 0. Alpha 0 means this goes away, this coupling, and this training decomposes, breaks down into individual training of personalized models on each local data set. Could this ever be useful, that we really let the models freely train, almost freely train on each local data set? What could be a problem? Bias? I mean, what could be a reason to pool local data sets and train one single model, like we have in this single model federated learning setting? So we enforce all model parameters to be the same, which essentially means we train one single model, but on all data sets together. So what could be the yes? Yes. So these local data sets, they might be too small. I mean, not too small in the sense of bytes, because I generate gigabytes of data on Google fitness tracker apps every year. So it's a large amount, but the information, the useful information for really tailoring a training plan for me might be very low. So the useful the effective size of the local data set for me is too small to train a transformer network with billions of parameters that would be able to tell me, tomorrow you should maybe eat only 2,000 calories or something like this. So really powerful, accurate models. For this, we need more training data. And this is where this coupling comes into play. This coupling of local model parameters is equivalent to pooling the local data sets for which we couple the model parameters. And this pooling means you have more and more and more training data to fit reliably train high-dimensional models. So that's why alpha very small is only useful when you have large enough local data sets, which might be in some application the case. You might have sufficiently large local data sets, like in this weather application. An FMI station collects data since 100 years. I don't know exactly, but FMI weather data is there for 100 years on a 10-minute scale. So a lot of data. Okay, any questions at this point? Yes. 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 Very good point. Yeah. So one argument against this making alpha large and coupling more and more local data sets, well, this pooling also means averaging. The more you pool into your training set, the more you train a model for an average person. So if you average over all patients, you train a model for the average person. So this contradicts this personalization aspect. So there's a sweet spot somewhere in between. And where this sweet spot is the task for the federated learning engineer or scientist to find out which alpha. And I try to provide you some theory in this course that could guide you to find the right choice for alpha. In particular, this alpha will depend on the network topology. So how many edges do you have? How many of those are connecting the right nodes, the clusters? And yeah, what's the weights, the edge weights? If they are large enough, then you have strong coupling between two pairs or not, or compared to small edge weights. Yeah. Okay, but let me just briefly rewrite this GTV minimization. It turns out that you find the derivation in more detail in the lecture notes. You can rewrite GTV minimization as, guess what, as a quadratic optimization problem. The GTV minimization amounts to minimizing this quadratic form, where you have here a block diagonal matrix plus alpha, and then the Laplacian matrix of the empirical graph, Kronecker product I times W plus, then we have another term, a linear term, Q1 transposed Qn transposed W. And this W vector is the stacked vector of local model parameters. So we have the local model parameter at node 1 up to the local model parameter at node n transposed. Okay, so far so good. So it turns out that, again, GTV minimization for, so yeah, this is a special case for local linear models. So when you want to train a local linear model, at each node, we want to find a hypothesis map that is a linear combination of the features. But this linear combination is different for different nodes. We want to learn a different weight vector at different nodes, or potentially different parameter vectors. These are the local model parameters at node I. Okay, and computing those using GTV minimization amounts to solving this or minimizing this convex quadratic function. And that's the same structure or the same type of problem as we have seen for linear regression and for ridge regression. So again, it's minimizing a quadratic function. Okay, so how would you do it? How would you find the minimum for this quadratic function? Sorry? Gradient, using gradient. Well, you could say this is the objective function, and you try to find the W such that the gradient, so the optimum is characterized by the zero gradient condition. So the gradient of this objective function at the optimal weights should be zero. And if you plug this in, you get the optimality condition. So let's call this matrix Q here. You get 2 times Q plus vector Q. So this is vector Q equals 0. And here we have W2. So this is the optimality condition. And you can then, of course, compute the optimal vector. You can solve this by minus 1/2 Q minus 1 times Q. This you will do in the coding assignment for a very simple setting. You will have to find out what this matrix Q is. Yeah, by the way, this matrix Q here consists of these local data sets, or these quadratic forms for the local data sets, which is 1 over mi times the feature matrix of the ith data set. So here we have the features at node I. Okay. And yeah, you will compute this solution using this formula. Does any one of you have doubts or is concerned about this approach? Well, Python is patient. So if you manage to stack the matrices and build this matrix Q in an NumPy array, then you can compute the inverse. Yes? Yeah, computing the inverse might be challenging because this might be, so the size of this matrix scales. So here the number of blocks, of diagonal blocks is n, the number of nodes in the empirical graph. And if the empirical graph is the empirical graph of Meta, or what's it called? Facebook or X, then this is billions or millions until billions of nodes. So very large matrix. This is what you want to avoid. But in the coding assignment, it's not billions, it's 100 nodes. So, and the feature dimension is 1. So this matrix here are actually then single numbers, 1. So this matrix is around size 100. So let's say it's not too big that it's hopeless to compute the inverse, but more fundamentally, what could be a problem with computing the inverse of a matrix? Could be impossible. It could not exist. That's the key question of every mathematician. Does a solution exist, or does an object exist that we talk about the whole time? Maybe it doesn't exist, but it turns out you can, in the coding assignment, it will exist. For some reason, I know it will exist. But in general, of course, this matrix Q is built from the features of data points, and features is wild data per se. Could be all 0. And if this here is all 0, the only thing that is left here is this Kronecker product. So let's forget about this Kronecker product. Let's say it's this, we have only one-dimensional parameter vectors. So we have here the Laplacian matrix. So this matrix Q would become the Laplacian matrix. Is the Laplacian matrix invertible for any empirical graph? No, it's not invertible for any. So it's always not invertible. So in this case, it would not work. But if the local data sets are nice, behaved, then this matrix is invertible, and then you can compute it. So this you will use in this coding assignment, but in general, I strongly recommend to use other methods to solve these optimization problems arising in machine learning and federated learning, which is using gradient descent. Gradient descent always works or can always implement it. You don't need to worry about questions like, is a matrix invertible? Gradient descent doesn't care. Yeah, but we will talk more about gradient descent next in the next lecture, next Monday, which will be in Zoom, by the way. Next week I'm traveling, so the lectures next week will be in Zoom on Monday and Wednesday. In Zoom only. Okay, but yeah, the last thing I want to briefly discuss here is the properties. So again, like for machine learning, where we used empirical risk minimization, we now formulated the federated learning problem as an optimization problem. So this is nice. I like that, because once in an optimization problem, it's a well-defined mathematical object, and we can do some solid analysis. But are the solutions any good? So even if we can use cool gradient descent methods that find the minimum, are they any good? So we need to do an error analysis or a statistical analysis. And I have sketched a simple such analysis in the lecture notes that I briefly summarize. So again, for error analysis, we need a model for the data points. Without a model for the data points, you cannot do any error analysis. You can just minimize the optimization problem. But you need some model to say something about the statistical properties of the solutions. And again, this error analysis is based on the simple model that the labels of each local data set are given by a linear combination of the features times some correct or true underlying weight vector. So this is this famous notion of a true model parameters. Somehow we have true parameters that generate the data, but this is too good to be true. So we need some error term, because life is not that easy. So we have an error term here that I call epsilon. Yes. So, and this error term is the intrinsic noise in the labels, or the label noise. Yeah. I mean, this is just an assumption, but of course you could try to estimate this W overline using maximum likelihood methods. So there are statistical methods that allow to find a good model. But now I just propose it. That's the easiest part in mathematics. So you just define some model. And let's see what once we say that the data is generated like this or satisfies this model, how much is the deviation of the solutions? So the GTVMin solutions are W hat. So what's the deviation of the solutions from the true underlying parameter vector? And it turns out we cannot directly say something about this, but one component of this error. So one component of this error is the variation or the variability of this learned parameter vectors. So this term that is left over once we subtract the average. So if we subtract the average of all learned, so this is kind of the DC component or the mean, all that is left is the wobbling in the learned parameter vectors. And this wobbling should be zero, because if we assume the true underlying parameter vectors are all the same. So this is one, this proposition 3.1 applies to this setting where all local model parameters are the same. So this is the single model federated learning setting. And in this case, one error component is given by this variation part of the learned parameter vectors. So in general, this error term is this term plus something else, but the something else I don't care for the time being, and to keep the analysis somewhat simple. And in proposition 3.1, I state that the sum of, so this I call this kind of this variation term of the learned parameter vectors I call W tilde, and this W tilde summed over all nodes is upper bounded by 1 over lambda 2. So this is the famous eigenvalue, lambda 2 of the graph Laplacian times alpha. This is the regularization parameter times the errors in the signal model. Okay. So this bound has 3 components. This is the intrinsic error. You can never expect, or you typically cannot expect, to have a smaller error or estimation error of any machine learning algorithm than the intrinsic error in the noise. This is somewhat the intrinsic uncertainty or variation. You cannot beat this. But you can damp this somehow, this variation, by forcing the change over edges in the empirical graph to be smaller and smaller. And this you can do by making alpha very large. So here this shows that if you make alpha large, then this variation of local model parameters becomes smaller and smaller. I mean, this is intuitive. If you make alpha large, then W hat goes to 0. And this means in turn that the W or this W tilde goes to 0. But if we insert here the definition, this means that for all nodes, W hat E is or becomes more and more equal to the average over all W hat I. So if you make alpha large, this deviation of the learned parameter vectors from its average over all nodes becomes smaller and smaller. So this is a precise quantitative formulation of what I told before, that if you make alpha larger and larger, you force the learned model parameters to be more and more identical. And here you have a precise upper bound of this variation of local model parameters. Okay. And yeah. Just briefly mention also, you have here a product, the product of alpha. This is a tuning parameter of GTV minimization, like the alpha in ridge regression, and lambda 2. So this is a property. This, as I said, this measures the connectivity of the empirical graph. So here you see how the empirical graph influences the behavior of GTV minimization. The larger lambda 2, the more you enforce equal model parameters everywhere. Does any one of you have heard about special graphs that have the maximum lambda 2 when you fix the total number of edges? So it seems if we want to learn the same model at all nodes, so this is what we want in single model federated learning, and there are many useful applications for this. If we want to have the same model at all nodes, we should have a large lambda 2. Does any one of you know the types of graphs that have a large lambda 2? That have a high connectivity, in other terms? Yes?
Maybe like fully connected graphs where each node connects to all other nodes.
Exactly, yeah. That's the best solution, yes. So you would have, with 3 nodes, you just connect every 2 nodes. But this, of course, one problem with this complete graph is the number of edges scale with number of nodes to the power of 2. So a lot of edges, and each edge carries computations. So number of edges is roughly proportional to number of computations. So what you typically like is you want to fix the degree of each node to be 5 or 10, and this is called a sparse graph. So, and I forgot to say, under this additional constraint that you require a graph to have a given maximum node degree. So each node can have at most 10 neighbors. Which graph has the largest lambda 2? Which type of graph or family of graphs? Did anyone hear about this topic or something similar? So I just started to look around because it comes out of the analysis that we want this lambda 2 to be large for certain applications. And my research so far brought up the terms expander graphs. Did anyone hear of you about expander graphs? They seem to be a special type of graph. And in particular, Ramanayake Yun graphs, Ramana-Yun graphs. Hopefully I spell this correctly. They seem to be distinct in having maximum lambda 2 for a given pre-specified number of edges, so to say. So when you want to design or engineer a network for federated learning and you want to learn the same model for all nodes, then use an expander or a Ramana-Yun graph. Pretty cool. Okay, that's what I wanted to tell you about GTV minimization as our main federated learning principle in this lecture. The next lecture then on Monday, we'll talk about gradient methods. This is our bread and butter tool to solve learning problems like GTV minimization, like ridge regression, like linear regression. And we will then see in the next lecture on Wednesday how this gradient descent, if we apply gradient descent to GTV minimization, naturally leads to distributed federated learning algorithms, which in the end do message passing. So you pass messages over these edges in the empirical graph. Okay, any questions at this point? Yes. Yeah, so as I said, these empirical graphs, they are undirected by construction, but you might bring in this directional aspect if you somehow unfold the message passing over time. So you would have a separate empirical graph instance on different time instance, and then you get this direction by connecting the right nodes in consecutive time steps. That's how you could bring in directionality in this federated learning algorithms, but per se, it's really meant for any kind of symmetric types of computations. But I do not say that this is the best and sufficient for all applications. In some applications, you want to have directed empirical graphs, but these are not covered in this lecture. Any other questions? Okay, thanks for your attention and have a nice evening.